I'm Roland Minton. These are some of my favorite math stories. In this episode, mathematics is chaotic. We will look at the function x squared minus 2 and some of its surprising properties. Wait. Don't shut this down yet. It may sound like basic algebra, but this function will lead us to some insights in weather forecasting, epidemiology, heart disease, and a controversial Disney video. We want to know what happens when we iterate functions. We'll start by iterating the function x squared, starting at x equals 1/2. 1/2 is 0.5. Let's do it in decimal. And we'll plug it into the function. 0.5 squared is 0.25. Iterate means we put that result right back into the function. 0.25 squared is 0.0625. And again, 0.0625 squared is about 0.0039. What happens if we keep going? Well, we get smaller and smaller numbers. The values are getting closer to 0. We'll say that this iterates converge to 0. What if we start at x equals 1? Plug it in. 1 squared is 1. Put it right back in. 1 squared is 1. Again, the iterates are stuck on 1. We'll call this a one cycle or a fixed point. X squared actually has one other fixed point. Can you find it? We'll come back to that later. Let's start with x equals 2 and see what happens. 2 squared is 4. 4 squared is 16. 16 squared is 256. This time the iterates keep growing, and we'll say informally, they blow up to infinity. And it turns out that those are the only possibilities for x squared. Converge to or repeat a fixed point, and 0 was that other fixed point, or blow up to infinity. That's what mathematicians want to learn. What is the complete list of possibilities for some process? Let's change functions. Do x squared minus 1, and we'll start at x equals 0 first. So along with squaring, we'll also subtract 1. 0 squared minus 1 is negative 1. Negative 1 squared is plus 1, minus 1 is 0. Then 0 squared minus 1, negative 1, and we're stuck repeating those two numbers. We'll call it a two-cycle, negative 1 and 0, a new type of behavior. Let's start instead at 0.5. 0.5 squared minus 1 is negative 0.75. Negative 0.75 squared, we'll now see why computers are so important in this field. Let's use a computer or calculator. The sequence looks like from negative 0.75, we're going to get negative 0.44, negative 0.81, and so on. Those last two numbers, very close to negative 1 and 0. And it turns out if you keep going with the sequence, they'll get closer and closer and converge to the two-cycle negative 1, 0. Now this function also does have a fixed point. If you want an algebra challenge, show that 1 plus the square root of 5 over 2 is a fixed point for x squared minus 1. So this function can converge to a two-cycle, repeat a fixed point, or blow up to infinity. Now we'll get to our function of interest, x squared minus 2. Let's start at 0. 0 squared minus 2 is negative 2. Negative 2 squared is 4, minus 2 is 2. 2 squared is 4, minus 2 is 2. We're stuck repeating a fixed point, 2. Let's start at 0.5. 0.5 squared minus 2 is negative 1.75. And we'll look at some more outputs for computers. There's some positives, some negatives. Not real sure what pattern is going on there. Sometimes, though, the pattern takes a while to reveal itself. So let's go all the way out to iterates 100 through 105. And still not much pattern. The last two maybe look a little bit like 0 and negative 2, but that's an accident. It does not continue that direction. In fact, these iterates never repeat. They just bounce around between negative 2 and plus 2. Now, never repeating without blowing up to infinity, two of the properties of what's called mathematical chaos, which is what we've got here, a new behavior. Well, x squared minus 2 does have fixed points, and it does converge to chaos. What else can it do? It can do a two-cycle, actually. The values are negative 1 plus square root of 5 over 2, and negative 1 minus square root of 5 over 2. More importantly, it has a 3-cycle, 3 numbers that rotate around. The precise values are very messy, but approximately negative 0.445. If you square that, subtract 2, you get about negative 1.802. Square that, subtract 2, 1.247. Square that, subtract 2, you're right back to negative 0.445. So the existence of this 3-cycle, it turns out to be very important because of a result called Sharkovsky's theorem. If a function has a 3-cycle, then it has cycles of every size. That's worth thinking about. So there exists a set of, for example, 132 numbers between negative 2 and plus 2, such that the iterates cycle through those numbers and repeat. And you can replace 132 with any positive integer you want. So, for example, there's a different set of numbers, 861 of them, for example, that cycle through the function x squared minus 2. And any other number in the millions, billions, trillions, it's a lot of repeating numbers. And yet, what most iterates do is that mathematical chaos, an infinity of numbers that never repeat. That combination of an infinity of numbers never repeating, that's the most common, but also an infinity of numbers that do repeat. Very interesting. So would you say this is highly ordered or highly disordered? Probably a good answer is yes. We won't have time to get into it, but there is an amazing progression of behaviors as you move from x squared, remember that wants to converge to a fixed point, to x squared minus 1, wants to repeat a 2-cycle, to x squared minus 2 wants to do mathematical chaos. And with numbers in between, the 0, 1, and 2 that we're subtracting, you get a wide range of other behaviors. This progression is directly related to an innovation in heart pacemakers. So oversimplifying, the pacemaker is able to recognize a slippage from a healthy dynamics, symbolized by x squared, to less healthy dynamics, like x squared minus 1, and pushes the rhythm back to a healthy regime before it reaches atrial fibrillation, symbolized by x squared minus 2. Let's do a couple more connections to the real world. Lemmings are really cute little rodents with large fluctuations in population. If you know a quote fact about lemmings, it's probably that they control population booms by mass suicides, blindly following their leaders off of a cliff. Now this actually is a myth perpetrated by a cruel Disney video. The lemmings were pushed over the edge of a cliff by crew members just off screen. But lemmings do have large fluctuations in population. What can explain these bursts? A simple population model to take this year's population x and predict next year's population is 4x times 1 minus x. A species with a large reproductive rate, such as the lemmings have, could be modeled by such a function. This function has the same properties in iteration as x squared minus 2, except that its values bounce around between 0 and 1. So the most common outcome in iteration is this mathematical chaos never repeating and bouncing up and down unpredictably. So those large fluctuations in population could just be the natural changes of a population that is mathematically chaotic. Chaos, it can actually be very natural. Mathematical models of infectious diseases can be very similar to models of population change. Measles cases show somewhat unpredictable fluctuations, as seen in this graph. A debate in the research literature is whether measles dynamics are naturally chaotic or not. The practical importance of answering this question is in prevention strategy. If the natural dynamics of measles are chaotic, then a brief outbreak could be followed by recovery without intervention, just the regular bouncing back and forth of a chaotic iteration. A short-term intervention could actually be counterproductive. Instead, efforts should be focused on changing the large-term dynamics underlying the disease, for example, through vaccination. In essence, trying to change the governing equation from the chaotic and hard-to-control x squared minus 2 to the predictable x squared. I bet that x squared minus 2 turned out to be more interesting and important than you expected.